Right, I will now present some guidelines regarding the general usage of TTK. For this, I will use this standard example, which is the toy example that is described in TTK's companion paper. So what you see here is a screenshot of ParaView. And here you recognize the pipeline browser that was introduced before and basically describes the sequences of processings that the input data goes through. In particular, in this example, the input data is a simple 2D terrain, which is a bit noisy. So to cope with the additive noise present in the data, the persistence curve, shown in the top right corner here, has been computed to isolate a threshold which separates noise from features. And what this curve says is that there's a flat plateau right here in the number of features for a localized interval of persistence threshold. And this means that if you simplify the input data within this interval, you will not lose many features. So it's a sort of stationary state which typically separates noise from features. From this point on, what is shown in this example is a very standard procedure that is used in the vast majority of the TTK use cases. So first, the persistence diagram is computed here at the bottom right to select the most persistent features, the most important ones. And then the data is pre-simplified such that only the persistent features remain. And after this point, any topological analysis can be carried out. And in this example, the Morse-Med complex of the data is computed, and we see the critical points with spheres, the separatrices with cylinders, and the segmentation of the data into the descending manifolds. So far, this example has been presented in ParaView, but TTK can be accessed and used outside of ParaView, and I will further describe this now. So each module in TTK is available as a filter in ParaView. And here, each filter is shown with a little green box in the pipeline browser here. So you can apply each TTK module to some data set in the ParaView user interface thanks to this filter notion. But each TTK module is also available as standalone programs, such that it is possible to replicate everything which is done in ParaView with simple standalone programs. So initially, each filter was associated with two standalone programs, a minimal VTK-based graphical user interface that you see here, and a command line program. But the graphical user interface is going to be marked as deprecated since we found that this was not very used by the TTK users. And the standalone command line programs, on the other hand, are fairly useful for batch processing or benchmarking. And here you have a screenshot of the screen output of the command line program down there. In addition to the ParaView plugins and the standalone programs, TTK is available as an API for developers. And we actually provide 4 different APIs. We first provide a ParaView-based Python API called PVPython. This is a plain Python API that implements the TTK features which are accessible within ParaView. So this is by far the simplest API, and it really mimics the content of the pipeline browser. So in particular, to reproduce the data processing pipeline shown in the ParaView interface, here which consists in computing the persistence diagram, pre-simplifying the data, and computing the Morse-Med complex. Well, all of this pipeline can be done in about 20 lines of Python. And an interesting aspect of the PVPython API is that such code snippets can be generated automatically by ParaView, as I probably mentioned before. For instance, if you design a data processing pipeline in ParaView and you are happy with it, well, you can export it automatically as a Python script, which will follow this API. So this API, as I said before, is arguably the simplest to use. It targets end users who want to batch process their data in a convenient and simple way. Since last year, we also provide a VTK-based Python API, which is for more advanced users and Python developers. In particular, this API provides more advanced functionalities to fully interact with the internals of each TTK module, and not only the output it exposes in ParaView. So this API targets Python developers who are interested in using TTK, but Lutz is going to provide more details about this. So for more advanced developers, in particular those who use C++, TTK is available with a VTK-based C++ API, which exactly coincides with the VTK-based Python API. So to reproduce the processing of the toy example with this API, you'll need about 40 lines of code. This API is the one that we recommend to use for C++ developers, especially for those developers who are already familiar with VTK. For those, this API will feel extremely familiar and natural. We recommend to use this API also if you are not familiar with VTK, as it is very convenient to use in terms of memory management and I/O handling and consistency and all. So for instance, a couple of years back, Will Usher and Ki Wu wrote a topology-driven volume renderer called TopoVol, which used this API. So if you do not wish to use VTK, we also offer a last C++ API that directly exposes the internal features of TTK in a way that is completely independent from VTK. So this is pretty much an API for these developers who want to pull a minimal amount of third-party dependencies, in particular who do not wish to pull the VTK dependency. So here, to reproduce the processing of our toy example, you will need about 100 lines of code. This is by far the most verbose API because there is a lot of low-level things that VTK used to take care of and that you now have to take care of yourself, such as I/O, memory management, and allocation, and so on. And for instance, as Martin will show, InVivo is using this API of TTK. All right, now we'll move on to the basic usage guidelines for PowerView. So under the PowerView user interface, most TTK features are available as filters, which are basic data processing units. And in particular, the TTK filters are arranged in some menus appearing at the bottom of the list right here. For bivariate data, we provide features to compute continuous scatter plots, fibers and fiber surfaces, Jacobi sets and Rip spaces. And here I refer you to the website for usage examples. TTK also provides an advanced PowerView Cinema support for the handling of databases of data processing artifacts. This is typically useful if you consider, for instance, large collections of data sets and you apply some topological analysis for each data set. If you want to store and manipulate in a convenient way the database of topological outputs, you want to use our Cinema features. We also provide a few features for dimensionality reduction. In particular, we integrate scikit-learn to support state-of-the-art dimensionality reduction techniques. This is particularly useful to handle high-dimensional data sets and project them down in the dimensions, typically 2D and 3D, where TTK is currently able to operate. We have a long list of filters in the MISC category, and these are mostly convenience features that we found to be useful when developing the core topological features of TTK. We provide a substantial amount of features for scalar data, including merge trees, contour trees, Marshmallow complexes, persistence curves and diagrams, critical points, rip graphs, fast distances and barycenters for persistence diagrams. And note here the presence of the topological simplification filter, which, as I said before, is pretty central to most TTK use cases. We also provide features for time-varying datasets, including critical point tracking and nested tracking graphs. And for uncertain data, we have a couple features, including mandatory critical points. Importantly, for each filter, you have an online help page, which is available. To access it, simply click on the question mark button here, and this will open the help page to the right. This page should explain in details what inputs are expected, what are the parameters, and how to interpret the output. We provide also a data package that contains all the data sets in PowerView state files for the examples shown on the website. So it's a great entry point to TTK because with this you can replicate everything that is available on the website and understand how the different pipelines were put together. We also have a number of video tutorials that explain on a step-by-step basis how to replicate the examples from the website. And Lutz will further discuss this, but TTK support in Python is fairly easy to use thanks to an Anaconda package. So as mentioned before, TTK is available with a Python API. You'll find the code for the toy example processing in the source tree of TTK under the examples subdirectory. and the Python code will be under the examples Python subdirectory. But in short, you have a block of code to compute the persistence diagram here for thresholding it, simplifying the data, and computing the Morse-Mach complex. You have the same example for the PV-Python API under the examples PV-Python directory, in VTK C++ under examples VTK C++, and for the C++ in example under example C++. So again, if you are a developer and you want to use TTK, we recommend that you take a look at these examples. Also, there is a companion Doxygen documentation for TTK, which resembles in this form the VTK documentation. We refer you to the website where you'll find a lot of additional documentation material and links to user mailing lists. All right, so now that you have a sense of how to use TTK, in particular in PowerView, we'll proceed to hands-on sessions where we'll show how to use TTK features in PowerView for concrete data analysis tasks. And this includes data segmentation, filament extraction, or topology comparison.